Okay, thank you. So I will speak in front of my computer, but just I opened my file in my computer, so it's easy for me to follow what I am saying. So thank you for your invitation, and good evening or good morning, dear colleagues, depending where you are. I'm glad to be in Australia for half an hour and take profit of the summer, while in Limoges it is a fresh winter day, thanks to Zoom. So today I will present a joint work with two Peruvian colleagues, Katrina and Zuniga, and the paper related to this conference has appeared in this fall in JOTA. The outline of my talk will be the following. First, I will present a short history about equilibrium problems. Then I will give some examples, then give tools and results. And if I have enough time, possibly I will speak about a system of quasi-equilibrium problems at the end. Okay, so this is a picture of my two colleagues. And the aim of this talk is to continue the study on existence equilibria and quasi-equilibria in the setting of metric spaces. The first appearance of equilibrium problems, as we understand them now, is due to Utley and Moore, and it was further developed by Bloom and Utley. They are conceptually connected to Kiefan's minimax inequality, which goes back to von Neumann works. The term equilibrium emphasizes the broad application that can be analyzed in this framework. Optimization, variational inequalities, fixed point theory, Nash equilibria, and some other. There exists a large literature about existence involving generalized convexity and generalized monotonicity assumptions. We can consult, for instance, the works by Bianchi, Pili, USM and Sosa, USM, Kassai and Sosa, Nasri and Sosa, Adjizavas, Castellani and Julie, Katrina and Garcia. Okay, let me give the definition of equilibrium problem. We consider a non-empty subset of a topological space X and F a B-function from C times C to R. And the equilibrium problem is a problem of finding an X in C such that F of X and Y is positive for all Y in C. Existence results go back to the celebrated Dastner-Kuratowski-Markusewicz theorem in 1929, and its generalization in finite dimension by Kiefan in 1961, and also its extension, the extension of Kiefan results by Bresis-Nirenberg-Stampacchia to a subset which is not necessarily compact by using a coercivity type condition. Nowadays, a great interest is given to the convergence analysis of iterative method to reach solution of equilibrium problems. Okay, so I put a picture of Kiefan taken in 1975 at a meeting organized by Stephen Simons in Santa Barbara to honor the 70th birthday of Kifan. And you see also another, two other famous mathematicians, Kakutani, which is famous for its fixed point theorem, and Jean-Pierre Aubin. And the Kifan minimax principle from 1972 reads as follows. Assume C is a compact and convex subset of Hausdorff topological vector space, and suppose F, the bivariate function F from C times C to R satisfies three conditions. F of x and x is less than equal to 0 for every x in C. For every x in C, the set of y in C such that f of x and y is strictly positive is convex. And for every y in C, the function f with respect to the first variable when y is fixed is lower semi-continuous on C. If these three assumptions are satisfied, then there is this x naught in C such that f of x naught and y is less than or equal to 0 for every y in C. Okay, now I want to speak about the Bresis, Nirenberg, Stampakia results. So Bresis, Nirenberg, and Stampakia, three famous mathematicians, with the goal to apply to variational inequality. In this case, the function f of x and y is equal to the scalar product between ax and x minus 1 when a is a monotone or a pseudo-monotone operators in the sense of Bresis. And the Fan's results was extended in this case by Bresis, Nirenberg, and Stampakia. And the theorem reads as follows. The assumption 1 and 2 of Kifan minimax inequality are satisfied, but then we have three other conditions. 3 prime, for every fixed y in C, the function is lower semi-continuous with respect to the first variable on the intersection of C with any finite dimensional subspace X. And whatever x and y in C and xy is a net on C converges to X, then this condition in red is satisfied. And finally, the last condition, there is the compact subset L of X, and why not in the intersection of L and C, such that f of x and y naught is strictly positive for every x in C and y naught, which is not in L. Under all these conditions, we can find an x naught in the intersection of L and C such that f of x naught and y is less than or equal to 0 for every y in C. And in particular, you have this inequality, the infimum over x in C of the supremum over y in C of f of x and y is less than or equal to 0. And the proof of this theorem is based on the Nassner-Kuratowski-Markusewicz theorem, which implies the von Neumann-Thion minimal principle and the Hartmann-Stampakia theorem. Okay, so Moscow introduced an implicit variational problem nowadays known as quasi-variational problem. Bloom and Dudley proposed a mixed version of Kifan's minimax inequality by perturbing the monotone objective B function f by a monotone term, and discover further problems such as non-convex and non-smooth Palagiotopoulos inequalities considered by, for instance, Shadley, Shbani, and Rayai. Also, Ait Mansour and Rayai studied for example, the quantitative stability of equilibrium problems, and relaxed generalized quasi-monotonicity and quasi-convexity were studied, for instance, by Castellani and Giuli, Adjizabaz, Bianchi, Kassai, and Pili, and many others. And iterative method for equilibrium problem were studied also, for example, by Mudafi and by also many others. Now I will speak about examples. The first example, let's C be a non-empty subset of Rn, H, and T, two functions on R, from the first from Rn to R, and the second from Rn to Rn. And you consider the minimization problem, which consists to find x in C such that h of x is less than or equal to h of y for every y in C. In this case, we use the function f of x and y equal h of x minus h of y, and the x bar solves the minimization problem related to h if and only if x solves the equilibrium problem. The second example is the Stampacchia variational inequality problem associated to an operator T and C, which consists in finding x in C such that finding x bar in C, xi bar in T of x, T is set-valued mapping, and such that the scalar product between xi bar and y minus x bar is positive for every y in C. In this case, you take the function f of x and y equal of the maximum of xi applied to y minus x over all the xi in T of x. And in this case, x bar solve the Stampacchia variational inequality if and only if x bar is an equilibrium problem with respect to f and c. Another example is when you consider an Hilbert space H and a set-valued mapping H from H to X star, which is 2H, and such that T of X is non-empty and T of X is included in C. Then we consider the fixed point problem, finding X bar in C such that X bar belongs to T of X bar. And in this case, you take this function f of x and y defined of the maximum of x minus c applied to y minus x over all xc in T of x. And also in this case, x bar solves the fixed point problem if and only if x bar is an equilibrium problem with respect to this function f. Also, another example, it contains Salo's point problem, which is defined as follows. You have two Hilbert space H1 and H2, two closed convex subset C1 and C2, and we say that X1, X2 is a Salo point of the bivariate function C theta defined on C1 times C2, if and only if this inequality is satisfied for every pair U and V. And if you set C equals the Cartesian product of C1 by C2 and F, the bivariate function defined in this way by using theta, then the equilibrium problem associated to F is equivalent to the Salo point problem associated to theta. Also, the last example I can give is related to Nash equilibrium problem. You have a finite index set I. Every player I has a strategy Ci, and you define C as the Cartesian product of all the Ci, which is a product of the strategy sets. For each Y, you define the function Fi from C to R to be the loss function of the player I, and which depends on the strategies of all the players. And F is defined by f of x equal the component of f of x are f1 of x, f2 of x, fn of x. You define C minus y, the Cartesian product of the Cj when G goes from 1 to n, but G is different from I. And also we define X sub I like this. So Xi is missing. And then for each X and Y, you set this, what is written in red, X of Yi as this. And we say that X bar is a Nash equivalent problem if it satisfies this inequality. Okay, and in this case, you can define a function, the behaviorate function f of X and Y like this. And again, we have that Nash, X bar is a Nash equivalent problem if and only if X bar solves the equivalent problem associated to f. Now I want to speak a little bit about the tool I need for the rest of my talk. I will speak about transfer lower continuity, transfer lower semi-continuous regularization, Eklund's variational type principle for B functions. Okay, so Tian and Zhu in Journal of Mathematical Economics in 1995 were interested in the question to know under which minimal condition a function f attains its maximum on a compact set. The set of maximum points of the function on a compact set is non-empty. The maximum correspondence is closed. And they introduced the concept of transfer lower continuity. And the definition of transfer lower continuity is the following. You take a function h from C, an extended real function h defined on C. It is said the transfer lower continuous, TLC for short, if for each y, x and y in C, such that h of x is strictly greater than h of y, there exists y prime in C and a neighborhood v of x such that h of x prime is strictly greater than h of y prime for every x prime in the intersection of C and the neighborhood of x. And also we have a concept of transfer weakly lower semi-continuity, WTLC for short, which is defined as it is written, if for each y, x and y in C, such that h of x is greater than h of y, there exists y prime in C and a neighborhood of x such that the h of x prime is greater than or equal to h of y prime for all y prime in the intersection of V and C. So the difference is that we have a strict inequality and then a large inequality. Okay, and they prove the following facts. If you have a compact subset of a topological vector space or for topological space X and F an extended real valued function, then F attains its minimum on C if and only if F is transferred weakly TLC. And also, but this not a sufficient condition without compacity. The compacity is important in the theorem. And another theorem, if C is a compact subset of a topological space X and F is an extended real valued function, then the set of minimum point of F over C is non-NP and compact if and only if F is TLC. So this is the definition of the the definition, classical definition of a lower level set. And we can prove that H is TLC if and only if we have this inequality between the level sets. And contrary to lower semi-continuity, TLC is unstable under addition. This is an example. If you take this function, whose graph is this graph, H and H and G are TLC, but H plus G fails to be TLC at 0. The function H plus G is defined like this. This is an example where you can see that the lower semi-continuity TLC is contrary to lower semi-continuity, TLC is unstable over addition. Now, this is a classical thing. You have a lower semi-continuous regularization of a function. Is a function whose epigraph is the closure of the epigraph of the function. Equivalently, it is defined like this. And it is well known, these facts are well known. In particular, the level set of the lower semi-continuous regularization of H at the level lambda is the intersection of this level set, of the closure of this level set at the level mu, where mu is strictly greater than lambda. And we can say that a lower semi-continuous regularization is well defined if H bar is strictly greater than minus infinity. And in other words, it means that H bar admits a lower semi-continuous minimum. And we have a proposition, if C is non-empty subset of a topological space X, and H is a function, then if H is TLC, then the H bar, the lower semi-continuous regularization, is well defined. Okay, this is easy. And if well known also, if C is non-empty subset of a topological space X and H is function, then the following holds: the infimum of the X of H of X is equal of the infimum of H bar of X over all X in C. Okay, and if C is a non-empty subset of a topological space X and H is a function, then if the argmin of H is equal to the argmin of H bar, then H is necessarily TLC. The following example shows that the converse of the previous results is not true in general. If you take this function, C in this case, we are in R. C is a set of positive rationals, and H is defined on C like this: 0 if X is equal to 0, and 1 over Q is X is equal to P over Q. So we can prove that H is TLC, and the argmin of H is 0, but on the other hand, H bar is a constant, is a function constantly equal to 0, and this implies that the argmin of H bar is all C. Clearly, the argmin of H is equal to the argmin of H bar when H is lower semi-continuous, but it is not true in general if the lower semi-continuity of H fails. Now, a Eklund's variational principle for B functions. Utley and myself and Bianchi and all, Aleš and Radulescu. Okay, the approach given in this result is based on the assumption that the equilibrium B function should satisfy what is called the triangle inequality property. So which is this property in red. And Castellani and Julie prove that if C is a non-empty closed subset of a complete metric space, XD, and F is a B function defined on the Cartesian product of C and C, if you assume that there exists a function H defined on C, bounded from below and lower semi-continuous, satisfying f of x and y greater than h of y minus h of x for every x and y in C, then for every epsilon strictly positive and every x naught in C, we may find x bar in C such that h of x bar is less than or equal to h of x naught minus epsilon, the distance between x naught and x bar. And also, we have that f of x bar and y plus the epsilon, the distance between x bar and y is strictly positive when y is different from x bar and y is in C. And just a remark, when f of x and y is equal to phi of x minus phi of y, this gives the original Echelon's variational principle. We can restate the Echelon variational principle in terms of lower semi-continuous regularization. So this is this theorem. If C is a non-empty closed subset of a complete metric space XD, and if H is a function bounded from below, for every epsilon strictly positive, and for any x naught in C, you have an x naught at in C, such that these two inequality hold. And theorem EVP through theorem, the last theorem, are all equivalent. Okay? And as a direct consequence, we have this theorem. Let C be a non-empty closed subset of a complete metric space. F a bivariate function defined on the Cartesian product of C. Assume that there exists a B function J, defined also on the Cartesian product of C, such that F is greater than J. J is bounded from below and lower semi-continuous with respect to its second argument. J vanishes on the diagonal of C. J satisfies the triangle inequality. Then, for all epsilon strictly positive and all x dot in C, you have an x hat in C, such that these two inequalities in red are satisfied. Okay, the second inequality is satisfied for every x which is different from x hat. Sorry.
Excuse me, Michel.
Yeah.
Could you please wrap it up? Because
okay. Okay.
Thank you. Thank you.
Sorry. So now I will skip this definition. Cyclically monotone operator, which goes back to Bernke, Kasai, and Pini, which extend Rockefeller definition, monotone B function, pseudo-monotone B function, and okay, I will try to go. I'm sorry, I was not enough fast. Now you have the definition of equilibrium problem, as I said before. In similar way, we can define the mean T equilibrium problem, okay, which is like this. And okay, and also the concept of quasi-equilibrium problem. Quasi-equilibrium problem, now you have a set value mapping K from C to C, and C a subset of Rn, and F a B function, And the quasi-current problem is the problem of finding x in k of x, such that f of x and y is positive for every y in k of x. Okay, so I'm sorry. So now, if from results, if C is a complex subset of x and f is a bivariate function, if there exists a TLC function h satisfying this inequality, then this equilibrium problem is related to f and c is non-empty. Okay, and this result was given by Castellani and Julie, but instead of considering transfer lower continuity of H, the author uses only lower sub-continuity. And okay, and we have also a corollary, which is the following: under the same condition, the Mentive equilibrium problem related to F and C is non-empty. Now, I think I have no time to go to quasi-equilibrium problem, but we have some results also in this of this type for quasi-equilibrium problem.
It would be great if you could conclude, Michel. Thank you.
Yeah, I just give the last result, which is the following: if C is the non-empty closed subset of a complete metric space, and if K is a self-valued mapping, F is a bivariate function, you suppose that the fixed point of K is compact and non-empty. There exists a bounded from below function H satisfying this condition, and you suppose that also this condition is satisfied, then the quasi-equilibrium problem is non-empty. Okay, and I will skip this, sorry, and go to the conclusion. Our aim was to study the existence of equilibria and quasi-equilibria in the setting of complete metric spaces. We achieved this goal by using the Eklund variational principle by dropping usual convexity assumptions. Our results extend many results that can be found in the literature, for instance, Castellani and Julie. In addition, we also proved the existence of solutions for systems of quasi-equilibrium problems in the setting of metric spaces. Further research could be done regarding other types of transfer continuity, such as transfer weakly lower semi-continuity and quasi-transfer lower continuity. Natural extension of this work to generalize Nash equilibrium problem quasi-variational inequality could also be considered in the future. Okay, the paper related to this is the following one. We use Tian and Zhu paper, Bloom and Nutley, Castellani and Julie, and many other papers. Thank you to all the organizers. And since I am the last speaker, I would like to thank all the organizers for having organized this new edition of WOBAT, despite the sanitary condition due to COVID. Many thanks to Nadia, Min, Rainier, Andrew, Alex, Vera, and Julian.